Hello, welcome to the stream today. We're going to continue our work with the video filtering. I know that I said we were finished, but I had a few ideas. I want to push the system a little bit further to see if we can get these ideas working. I feel like we could have some cool configurations. And other than that, I feel like I'm first going to show you what I have on screen. So let's see, if I bring this into view. So, lift this up a little bit. So let's talk about this guy. So here we have a squirrel. Squirrel. I feel like you guys should see it like I do. Let me play around with our joint camera real quick. Oh, so that is. And let's flip it. Okay, so you see it like I would see it. What happened there? Okay, so we have the Squirrel Acorn FPGA. This is an RTX 200T. I currently have one plugged into the computer under Windows, and so this program reads the first 3, 4, 5, 6, 7, 8. First 8 words from the DDR that's currently on my design. So over here, we're going to XSDB. Over JTAG, we're going to write to the device. So we go to targets. It thinks about it. Why is it taking so long for this one? Enter. Okay, so we have 2 targets. We have 3 targets. We have the Arty board, the 35T. We have a 200T, which is the Squirrel in the PCIe slot, and then we have a Vertex UltraScale 9P, which is the VCU 1525 that I'm playing around with. We are going to look at target 4, and then we're going to write to the DDR, which is at this location. Well, first, we'll just do a quick write. We'll write 10 times. Now, if we read here, we have A over the places. And we want to do dead beef. So we'll go over how to do this more in the future. But currently I have an FPGA in a PCIe slot. I can write to it in JTAG. I can write to it in PCIe. So I have this really cool communication. And we're going to work on developing that further. So one of the most important things about using a PCIe one is your PCIe driver on your FPGA can't go down. So you have to utilize partial reconfiguration through the ICAP, or internal configuration access port. So the future streams, we're going to look at doing a monitoring system where we can keep track of the temperature, because we don't want to go over temp. We want to look at keeping track of the temperature. We want to use the ICAP to do partial reconfiguration, and then eventually do fault injection for emulating soft errors that you would see in radiation doing that for my research. And then we're going to build some simple partial regions, and we're going to load soft core processors into those regions. And that's kind of where we're going to go in the future. And then we're going to design our own RISC-V processor and test it with other processor designs. So that's kind of later this week, but for now we're going to focus on our video processing that we have going here. So let's drop this down. Let's bring up Vivado. So what we're going to do is we're going to add RGB to our current setup. We're going to make the grayscale optional. And so we're gonna go to HLS. We're gonna make it grayscale optional. Then we're going to be able to do different filters on the RGB color scheme. So we could do maybe like a blur on one color, an edge detection on another one, or 2 different edge detection with 2 different colors. I think it's gonna be really interesting. I really like the idea of it. So we're gonna go to this guy. Maybe we can taskbar. Let's see if we can minimize. Yeah, let's minimize that guy. We can give you guys a little bit more space to view. And way. Okay, so let's launch the SDK first. Yeah, I know it's outdated, don't worry about it. Okay, so now since that's up and running, let's export the hardware. That's going to override it, and then our SDK is going to be, it's going to get sad face. Export is done. You export the hardware, right? Export hardware. With bitstream. Yes, I want to read. Right. Okay, we overwrote it. This usually gives me a, it yells at me. Let me look at the bit file. Properties, when was this bit file generated? June 20, 6:11 p.m. I think that's the one we want. Go find out when the original one was created. Not sure if our thing is updating correctly. Stream, DDI2, down to runs, location, versus bit file. That one wasn't done, so maybe that is a new one. Interesting. Well, what we'll do is we'll program it from this guy. Open hardware target, and target, auto connect. Yeah, that's the right one. Let's program it with yeah, this guy. Okay, now that's programmed. I'm going to bring our little camera over here so I can see what's happening. And we turn my screen over to HDMI, we should have a black screen. Actually, no, it shouldn't even be on, right? So let's run this guy. Cancel. Yeah, let's go run configurations. Apparently, doesn't know which FPGA. Not program the FPGA. Hardware platform, FPGA. I want it on the Arty. Okay, is that good enough? Run. Okay, so we ran it on the Arty. I can see if HDMI is working. Okay, HDMI is working. So we can go here. We can cd c/xup cd stream cd image proc. Then we can do a memory. Or we're gonna do a target. Yeah, we got the right target. Cool. Let's dial the data of test000.bin. We want to dial that into DDR. Okay, cool. Oh, I should show you guys what's happening on the screen. Nice. Let's rotate you. So we have a picture there, and now if we open term, oh, a lot of serial ports. I feel like it was 10 last time. I guess it was 10 because the way that reacted. Serial ports, we want new setting, terminal, let us see auto 0 1 identity. Weird. So it seems to have reprogrammed. Weird. So let's put it in again, I guess. Not sure, but we have our different Okay, so there we go. There's our different images. Okay. I have to. Okay, let's see how that looks to you guys right now. Okay. There we go. So we have that. Now we're going to do the 3 different colors. To do that, we need to pull up the HLS core. Alright, so let's pull up the HLS. And then we're going to redefine what happens in our design. Are we doing that? Let's get back on the FPGA. Bring this guy over here. I'm gonna get a kernel. So I want to split up into 3 different colors. So this is gonna be really fun. So currently these are of unsigned chars. We want those to be pixels. So where's the pixel data type defined? Pixel type. Let's just do a struct RGB pixel and RGB, right? You know what? Let's do something different. RGB. Let's make these line R, line G, line B. So we're gonna have a line, our data set just for the red color, a data set just for the green, and a data set just for the blue. And oh, we already have an RGB type. Yeah, let's do that instead. So let's go reverse all this. Do have an RGB type like I use. So we're gonna do RGB type, and what we're gonna do and yeah, we're just gonna do .r here. Oh, dot R dot R dot R dot R, and this is going to be return the red edge. Okay, so we have that worked out. Let's see. Let us see what we build then. What is our error that we have? Oh, yeah, we need that. Take that. Okay. So now we're gonna have red, and then we're gonna make a green and a blue, and then at the end we'll have an option to do a grayscale filter on them. Okay, that's exactly what we want. So where's the buffer? We're going to call that buffer R. We're going to buffer G, buffer B. Okay. So now we need to do some temporary values. So we need RGB temp 1 is going to equal this. So we're doing this so we only limit it to one read. We have to help the system understand okay. Oh, we don't want that. We want now it's giving the grayscale color. We want to do that. So 1, 2, and 0. 2, 0. And 0, 1. 0, 1. We're gonna test it real quick. Okay, so let's build this HLS, see what happens. So we're using HLS to do some video filtering, and we got to do just the red color. Now we're going to do it so it does all the colors. So now, okay. So we have our colors. Now let's do our, so this is all going to be G. I think we just need to change the temp to 2 and 0. We're going to do 0 and 1. So we've done the green color. Now I'm going to do green edge. Okay. Hopefully this doesn't use up too many resources doing it. See, okay, we're still doing good. So now let's do a blue. Oh, I was not there. So here's another blue one. That should be good. Create a blue edge. So yeah, let's run synthesis on this. Okay. Now comes the question, do we want to do grayscale before or do we want to do grayscale after we do the processing? I'm trying to think what would be interesting. I don't know. We could add a thing in here, a statement that grayscales that. We could have a thing in here that grayscales that. Well, it's built. Let's do a grayscale here. So pre-processing grayscale. So we're gonna do char. Grayscale 0. Now this is if grayscale equals 0. This would be the else. So we're gonna want a char gray equals unsigned char. Yeah. Signed char. And then we're just going to add it to all the colors. Temps.r equals gray RGB. Okay. Let's make sure that didn't confuse the thing. And set this, and then we're going to do a set of controls per design. Okay. Yeah, so we're good. Now let's do a struct. We're just gonna call this filter control, and basically it's gonna be these things. Okay. So we're going to have a filter control, and it's going to be, oh, I have the grayscale at the bottom. Let's put this guy at the bottom. And filter control, we're going to call him red. Red control, not equal 0. And we're going to delete that. We're going to have a green control and a blue control. And red control. These things should be red control dot that. Green control dot. Blue control. Okay, so we have our 3 different controls. We can do 3 different filterings. And then add them to different colors. Grayscale. Oh. This one. I think we're good to go. Let us run this guy. Then deploy the IP, look at the driver software, get it building. Probably won't have time today to look at it. What is it? 808. Maybe we can get it building. Okay, we have an error. Let's go figure this out. I'm curious. Use of undeclared kernel. Oh, we want green.kernel. Yeah. Two errors. And now. Oh, my bad. So we have controls, kernels. Just making sure that it doesn't go to an array, but it's completely accessible throughout the design. We're doing good. We're doing good. 41 cycles still. Sweet. It says it'll take up half the design. I don't believe it. Find out, I guess. Okay, so let's package this up and see if this builds on the FPGA. It may not. I hope it does. I really hope it does. We may have to shift to a more powerful FPGA to be able to run something like this. Or try to do it in hardware. If we did it in hardware, it probably wouldn't be too bad. I don't feel like if I did this in handwritten HDL, it'd be pretty simple. okay. I finished exporting the driver. So let's look at the driver software. I want to see what we're working with here. Okay, so our register base has changed dramatically. I'll have to edit that so it works in the same. And the grayscale is at the very bottom. It starts off at 0. Look at all those controls. So that's great. Now let's see if this will work. And let's open our block diagram. Let's see if we can actually place and route this design. We may use too many resources. We'll find out. It'll be fun. So we're going to refresh the IP catalog, upgrade that. Skip that for now. I think we're good. Didn't change any of the inputs or outputs. Yeah, looks good. Let us validate this, save it, then we'll synthesize it just to make sure the synthesis thinks it'll fit in the FPGA. And the synthesis is close to 100%, it may as well more. We can try optimization to see if it works. Save it, rerun. Okay, we're just going to run synthesis by itself. Okay, we don't need to generate that. It already has cached results. Maybe we can start updating the software while we wait. Well, I don't want to update the software until we are confident it'll probably fit on the FPGA. But I'm thinking for controls that we'll do QWE will change between RGB, and then we'll have the same channels, and 0 will be able to turn off a channel. And this way we could also actually try affect how the color is seen. Interesting. We put the blue edge on the last thing, because if we didn't do that, it'd be sad. Okay, blue edge is there. Good, that's good. Happy with that. So all it's doing is running this filter, and we might get a good guess of how much LUTs and flip-flops it says. So let's see what the difference is. So here, our beautiful HLS tools, which I feel like overestimate greatly, think it's going to take 20,000 LUTs, which is apparently half a design. So if we go to Vivado, and we can just look at that log real quick as it builds it. Not terribly interesting at the moment. The question is, how much bloat do we actually have? Synthesis finished. Cool. Design finished. Okay, that finished, I think. Yeah, look at this. So we went from 20,000 to 12,000, and then we can probably do further optimization inside the implementation stage. So that's pretty good. Again, that's a lot better optimization wise. Let's go synthesis. That will work on stuff. Okay, so let's open synthesize design. Actually, no, we're just going to view report. And actually, no, okay, so we'll go open the synthesize design and get a utilization report. Okay, while we do that, I'm going to see. So, first one has an offset of 10. Second one has an offset of 70. Third one has an offset of D0. And then we can configure these off, those offsets, all the way down to upper shift value. And we'll make defines this time. We won't be our magic number madness. Okay, this should be done soon. So if we go to the SDK, we can maybe start working on this. Let's do some defines, right? We're gonna do a define, we'll call it red red control, maybe 0, 10. G, B. Define. I want to do a macro for this. Okay, let's do a report, utilization, go for it. I wonder how much you're gonna say we're using. That'd be fun. I mean, we could do K0, K underscore 0. I'll probably do a macro for this if I wanted to. That's 9, so we're gonna do 8, 1, 18, 28, oh no, 20, 28, 30, 38, 40. Let's go see if the top one is 50. Okay, that should work. Here, utilization. So looks like we're about 800 LUTs over. I think we could optimize that out. Ooh, we have 52 block RAMs. Where are these block RAMs coming from? In the cache. Local memory. We could dumb down the cache size. We definitely need to dumb down the cache size, which would probably help. Okay, this processor doesn't even need cache. It's not really accessing the cache memory at all. So let's go back here. That will give us some free space. Our processor is not using caches whatsoever. Oh, that's really big. See if we can get this. Nope, it does not want to fit on the monitor. Okay. There we go. Current settings. Let's not use instruction data caches. Hit OK. Just want 2 masters. Okay. Not smart enough to do that. That's okay. Microblaze. Yeah. That's all good. Run connection automation on what? Okay. Then let's go here. Address editor, microblaze. Our memory we have it set at 64K. We do not need 64K there. Let's set that down to 32. Okay. Now that should give us some more wiggle room both in VRAMs and in LUTs and flip-flops. Yeah, that's fine. That's fine. Save it and let's go straight for generate bitstream. Okay, back to SDK. So the next things we have at 58, 60, and 68, we have shift value, define shift value be 48, pound define 58, is that what we got? Okay, and then lower limit 50, upper limit is 58. So and let's first, we're going to do a case 0. Oh, we probably should have the base address somewhere. I'm going to blanket 0. And then what's gray? Gray is all the way down here at 130. So we'll just do a quick. We'll do just what we call gray enable, and it's gonna be 130, and we'll have it bit flip. Like we'll read the value and then flip it. So let's go over. So we're going to say int channel equals RGB R control. Where do we? I find so terrible. This should be all caps. Okay, and we're just a case Q. And that's all that's really going to do. Let's do that, right? Oh, let's call it red channel. And we're going to do WE green channel, blue channel, green control, blue control. And then we're going to do G. And first off, we're going to read it. So first we need to read the location. So we're going to be like int gray status equals I need to have it outside. Okay, so I guess we'll do right here. We'll do int gray status is 0. Okay. See how Vivado is going. Right off, that's good. Let's get base address. Define function, I don't know, fbase, or let's call it base. Okay. Plus gray underscore e. If gray status 0, so we're going to enable grayscale. Else, I'm going to disable it. Disable grayscale. I want to enable it. Okay, so this is definitely shift value. Base plus panel plus shift value. This is what's going to be k underscore 0. K underscore 0. One, two, three, 4, 5, 6, 7, 8. Seem to have missed. Zero, 0, 5, 0, 0. -2, -1. 0. 1, 1, 1, 0, 1, 0, -2. Tossing. -2. 0, 0, 0, 1, 2, 1. There's our other Sobel filter. 1, 0, -1, 2, 0, -2, 1, 0. Okay. 1, 2, 1, 0, 0, 0, -2. The fun one. 0, 1, -2, 0, 2, -1, 0, 1. Okay. The value. Oh no, this is a fun one. 4, 1, 2, 1, 2, 4, 2, 1, 2, 1. Okay, there's a blur. Okay, so that should be everything we need for now. So this is going to be upper limit, and this is going to be k_4. But we're going to want to do it for red control, green control, and blue control. Okay, I think that's everything we need for this software. How's our hardware coming along? Oh, our hardware's done. Let's go ahead and open Hardware Manager. Let's get the utilization. Ooh, 83%. That's nice. So let's go ahead and program it with our implementation top. And then we're going to go to SDK. And we'll hit this. So now if we go to our HDMI, so I'm not getting anything on our video. Scroll is right. Data is not coming through. Did we get our addresses wrong? Let's do a memory read. Oh, yeah, that will throw everything off. Let's try. A 3. What's 4? 20. So let's try 0 to 31. Not acting like I think it. Address editor. That's weird. Why is it acting like that when it should be matching this functionality? So 0 to 30. Now let's write to our limit is 68. 68. 68. 255. Let's try exporting it. Maybe the memory. Oh, I switch screens real quick. See if we can get this working. Okay, so let's update this. I'm going to debug this guy today. So we're going to go to run configurations. Let us program the FPGA where we're at it. Run. Okay, stuff didn't build. Let it build. We're going to go Xilinx, clean all, go clean. Okay, everything built fine. Programming the FPGA. And let's do a memory read here. FF1. Okay, so our address is RGB 10 plus upper can we write as 268? So that worked. Oh. 70 D, right? 70 and D 0. Okay, what is writing? Fine. Okay, that's good. Program the FPGA. Do that again. and read. Okay, which one is getting written to 20? Why? 20 is not that address. It's going to, well, I mean, assume we have takeoff. Okay. Let's do so now we just got, I guess, a software problem. 68. So let's take all of this out of the equation for a second. No controls. Hear me? No controls. And let's program this guy. $20. And can we just straight up, we're just gonna print out that value. Maybe I'm just maybe I'm just gone crazy and I don't. Okay, cool. Four eight 306. Run that. Okay, so let's just run with what, 50? A0. Will this help? Oh, it might be indexing too far. Maybe. $68. 1. Okay, so what I understand. So let's try this guy out. And did I change the settings. Grayscale equals 1. Like it didn't get stated. Tools. Report IP status. Why is it not working? We're only getting kind of a white screen right now. Probably show you guys. Yeah, I mean, red, buff red controls. You know what? We're gonna write it by hand, see what happens. So, I'm going to put this over here, and give me, so, do address 30. Address 30, we're gonna write a 1. And, well, first let's read what we got here. I don't know why it went to B0 as well. Like that. Now, what if we write to B0? Write A0 to B0. Something's up with our memory writing ability. I don't have enough address space for it. So we're having an issue where the address is writing over several locations. It didn't get upgraded with the proper spacing. Oh, did I source this and this is actually doing a different location? The catalog, photo, kernel. Let's go here. bravado synthesis. B, 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 G. The memory's just not reacting the way it should. Okay, so let's say we do a memory write to 0, 0. Right to 23. Let's write dead. Dead. Okay, that makes sense. It shouldn't do that. We write it to 10. And we do a read. EF. EF. See, it's writing over multiple locations. That's not what it's supposed to do. Okay, so I'll play around with this and I'll see if I can get it working for tomorrow's stream. But yeah, thanks for watching. I will try to get the working out and we'll talk about the issues and how I debugged it. Thanks. See you guys tomorrow. Bye.